Problem 35. If the density function of x is f of x equal to 1/2 between -1 and 1 and 0 elsewhere, what is the probability density function of y equal to x squared? Okay, problem 35. We're given that f of x is equal to 1/2 and we want to find the probability that y is equal to x squared. So we're going to solve this two ways. Here's the first approach, where we look at a cumulative distribution function for y, and y is equal to x squared. So we want to find the probability that y is less than little y, which you substitute in x squared for y. Well, you take the square roots of both sides, and when you take the square root of both sides, it's a plus or minus. So technically you're in this setting. And then since it's a uniform distribution, the probability is just this for the cumulative distribution function. It's the probability we're less than that, and then minus the probability we're less than that. So now we need to take the derivative of this cumulative distribution function to find the distribution function. So when we take the derivative of this, we take each piecewise, so that's 1/2 times radical y plus the same, and it ends up being this is the density. Okay. Now for the second way to solve this, we start over here. We know y is x squared. So if we look at y equals x squared graph, it's this, and y is positive, so it's here. So there is no, so y equals x squared is not 1-to-1, so you can't set up a convenient relationship. So you have to break it up into pieces. So region 1, area 1, and area 2. And then if we y equals x squared is a 1-to-1 function, or we can create an inverse over each specific region. So then we find the density of this and add it to this. And the way that it works is we find a specific y, and then we have to back count. We have to find all the regions that we can have a 1-to-1 function going back onto x. And in this case, it's both regions. So we're going to always add both regions, and more detail on that in a second. So when we back solve for y equal to x squared, we get x is equal to plus or minus radical y. Now over this piece, x is equal to minus square root of y, and over this piece it's the positive root called the principal root. The Jacobian over this transformation is 1/2 2 times square root of y, and same for this. So then the density is the function, it's for each y in a region, we sum over all the regions where that y can be back solved in, which is both in this case. So we take each function, substitute in this value, so that'd be x or y, here, and that would be at x2, and we plug them into our density times the Jacobian. So it's 1/2 is our density, and the Jacobian is 1 over the square root of 2. So we add those together, and that adds actually to the same thing that we got up here. In this case, the first solution is probably a little bit easier, but it's problem 36. Suppose x and y are random variables with the expected value of y given x equal to -x plus 3 for all x, and the expected value of x given y is equal to -1/4 y plus 5 for all y. What is the correlation coefficient of x and y? Fun to do them both ways. Here we're given two linear functions, the expected value of y and the expected value of x given y. For these exams, they expect you to know this, that if you look at if y given x is a linear function in in this case x right here, this is always a setup. And deriving that each time would not be fun, so they expect you to know it. And it's sort of the reverse here. If expected value of x given y, it's always a function. If it's a linear function of y, then this is always a setup. And I'll put a link to a video that I have up that drives these to show you that this is indeed the form. But for the test day, you're going to have to remember those. And we want to look at the coefficients for x and y, because here's the coefficient for x, and there is a correlation between x and y. And this correlation is the same here. So we can grab two equations, and here the coefficient in front of y given x is, and let me double check that, is -1. And so this has to equal this piece, and this has to equal the -1/4, which is the coefficient they give for here. So then we can do some solving, some substitution, and then we get that this ratio of the standard deviations is 2 if it's y over x, and it's 1/2 if it's x over y. Then we can put that back into our equations to solve for the correlation, and we get -1/2 in both cases. Now, you could take these two times each other, and so this number times that, and then this times that, and these standard deviations cancel, leaving rho squared. You take the square root, and then you have to find out whether it's positive or negative, and you look at the sign in front of these coefficients. So, problem 37. Let x and z be independent where y has a chi-square distribution with 2 degrees of freedom and z has a normal distribution with mean equal to 0 and variance equal to 2. What is the distribution of w if w is equal to y plus z squared? So in problem 37, y is a chi-square with 2 degrees of freedom and z is normal with mean 0 and variance 2. So let's remember here's a note that if we have a standard normal, so if x is standard normal, and you square it, then you get a chi-squared 1. But z is not a standard normal. It's a normal with mean 0, variance 2. So to make it a standard normal, you have to divide by its standard deviation here. You know, subtract the mean, which is 0, divide by the standard deviation. So z over square root of 2 is a standard normal distribution. But then that means if you square this, so z squared over 2 is a chi-squared with 1 degree of freedom. And that tells us that z squared by itself is not a chi-squared. Okay, so then if we let w equal to a chi-squared with 2 degrees of freedom and something that's not a chi-squared, then w is not a chi-squared. So the answer is E. Number 38. Urn 1 contains 7 red balls and 3 black balls, and urn 2 contains 4 red balls and 5 black balls. After a randomly selected ball is transferred from urn 1 to urn 2 and 2 balls are randomly drawn from urn 2 without replacement, what is the probability that both balls drawn are from urn 2 are red? So problem 38, we have 2 urns. Urn 1, 7 black, 7 red, 3 black. Urn 2 is 4 red, 5 black. And we want to transfer 1 ball here into here at random. And then we're going to randomly draw 2 and then see if we want to know the probability that they're both red. So if we let x be that the number of red balls drawn, you know, I mean, the number of red colored balls on the 2 draws from urn 2, it can either be 0, 1, or 2. We're going to let T be the transferred ball color. So the ball that we pick here to here, which can either be red or black, and then if we know, you know, if we knew that, we could fill in T. So we want to find the probability that X is 2, that both out of 2 draws, both are red. Now we introduce this variable T, which is the color of the transferred balls. So if we try to find the probability that X is 2 and T is a red ball and T is a black ball, or T is a black ball, this probability doesn't change. But we do that so we can change this to a conditional probability of the marginal times X2. But in this case, if we know the color ball that's transferred, then we can easily calculate the probability that both are red. So I goes from red to black. So let's do red first. So assume we transfer a red ball to the color. So the probability that we transfer a red ball is 7 out of 10 because there's 7 red and 10 balls. And then the probability that we get 2 exactly is a hypergeometric. So it's 5 choose 2, 5 choose 0, 10 choose 2. And now we go to the black. So assume that we transferred a black ball, which is 3 over 10. And given that we transferred a black ball, the probability we have 2 red balls is 4 choose 2, 6 choose 0, and 10 choose 2. And that reduces to 44 over 55. Number 39. Let x and y have a bivariate density function which is proportional to xy for x between 0 and y between x and 1 and 0 otherwise. What is the regression curve of y on x? That is, what is the expected value of y given x for x between 0 and 1? So here, problem 39, we are given a density xy, which said it's proportional to xy, so we have to find that proportionality constant that makes it equal 1. So we sum over the whole region, and this should equal 1. So we sum over y first, plug in the values, integrate over y, plug in the values, integrate over x, plug in the values. So we get k over 8 equals 1, which implies k is equal to 8. So that's our density function. So then, to find f of x, and we need f of x to find the conditional density here. So f of x is we integrate out y of our joint density, and then we come up with 4x 1 minus x squared. So we take our joint divided by our marginal, and then we get the conditional of y given x, which is this. Now to find the expected value of y, we just integrate we add a y and then integrate it over all y, and we come up with this. Number 40. Suppose that the probability of being less than or equal to x is equal to 1 minus e to the minus x for x greater than or equal to 1, and the probability that x is less than or equal to y is 0 for x less than 1. Which of the following statements is true? That's the answer. So now problem 40, this is interesting. Note that when x is strictly greater than 1, not 1, strictly greater, f is a continuous function, which means that the probability that x is equal to any point is 0 because it's continuous for x. That should be x greater than 1. So this means that the probability that x is equal to 2 is 0. So that implies A, B, and C are not solutions. They can't be. So now we know that the probability that x is less than or equal to 2 is the same as the probability that x is less than 2 because it's continuous and the probability of a point is 0. So we're in this setting. Now if we look at the probability of 1, which is a boundary point, that's why we didn't say it was continuous. So if we're less than or equal to 1, that's the same as the probability we're equal to 1 because being less than 1 is 0. So these two are the same, which the probability that we're equal to 1 is 1 minus e to the first. So the answer is E. Problem 41. Let x be a random variable with density function f. What is the critical region for the best test of the null hypothesis is f of x equal to 1/2 for x between -1 and 1 and 0 elsewhere, against the alternative that f of x is equal to 1 minus the absolute value of x, where x is between -1 and 1 and 0 elsewhere, at the significance level of alpha equal to 0.1. So here we want to find the critical region for this test, and we're testing that is the distribution 1/2 or is it 1 minus the absolute value of x. So the way to set this up is to form it in this setting. If this is too small, reject. Now the probability that we're less than c given h, the null is true, that's alpha. And so to set this up, let's look at the probability that this density, which is this, plug in the null, and the alternative is less than c, which is equal to, you kind of multiply up and down and back, and you get the probability the absolute value is less than this. So that means that x is between the negative of this and the positive of this, which is this setting. And we get, since x is a uniform distribution, we know that this is the probability. And this is a picture of it. So this implies that c is equal to 5/9. But the probability means that we reject when x is between these values. So we plug in 5/9 to these values here, and then we get x between -1/10 and greater than that and less than 1/10 is the rejection region. So that's the solution. Number 42, let x1 through xn be a random sample from the uniform density f of x equal to 1/θ, where x is between 2θ and 3θ and 0 elsewhere, where theta is positive. What is the maximum likelihood estimator of theta? Oh, this is maximized. We want to maximize this function to find the maximum likelihood estimator of theta. So if we think about this value here, how can we make this bigger and bigger? N's a fixed constant, so to make this as big as possible, we want to make theta as small as possible, given these constraints. Now, these constraints say that the minimum value here has to be greater than that, the minimum of our sample, and the maximum of our sample has to be less than that. So if we let y1 be the minimum and yn be the maximum value in our sample, our minimum has to be greater than 2θ, which implies theta is less than y1/2. And the maximum has to be less than 3θ, which implies that theta has to be greater than this. Well, this constraint and this constraint is this. Theta has to be between these two values. Well, to maximize our likelihood function here, we want as small as possible theta. So to make this as small as possible and still be within our constraints, we set theta equal to this minimum value, which is the maximum of our data divided by 3. And so that's the answer.